Great, thank you very much for this opportunity and the question. So for a very long time, density functional theory, or DFT, which is a very powerful computer method to understand how atoms and electrons behave in materials, was the main tool that we use. It is fairly accurate, but unfortunately it's quite slow and sometimes also expensive. It can take sometimes from days to weeks, sometimes even a month, to run a very accurate calculation for a complicated material. Now, AI is actually changing that by acting as you can say, a smart helper or an agent. So once we teach AI models using lots of DFT results, then the AI can guess what the answers would be much faster, sometimes within minutes or even sometimes within an hour, instead of weeks. So this lets us actually test thousands or even millions of possible materials really, really quickly. Now, in my own work, for example, we've used AI to help to kind of spot or identify hidden atomic structures in metal oxides or the surfaces of these metals, and that we might have missed before. Now, we can dream bigger, so we can design completely new materials for batteries, even better catalysts for clean materials, and even more efficient, flexible electronics, all much faster than before. Now, if I were to introduce this to a lay person, it's like going from searching one book at a time in a really, really huge library to having a super fast search engine that understands the books. Great. That's actually a very good point. So, AI has been doing, or what AI has already made a very, very big difference. Typically, I would say it's summarized in two very large areas. Number one is to actually very quickly predict the basic material properties, like how much energy can a material store, or how well it can conduct electricity. And the second area is to screen huge numbers of possible materials to find the best candidate before anyone actually makes them in the lab. So now in my research group, we've used AI to speed up finding good catalysts for things like turning water into hydrogen fuel or making batteries last longer. Now, as regards to your second question, so the areas that's mostly untapped potentials are the things that will change over time, like how atoms move in a working battery, a bit more dynamic, and also, and of course, in very, very complicated places where different materials meet, like interfaces or heterojunctions. So right now, AI is great at what if snapshots, but if it's getting better at understanding real, moving, dynamic, messy situations. So I'm really, really excited about using AI to help design better interfaces for the next generation electronics and even cleaner energy devices. And that's still a lot to discover there. Yes, definitely. So I think you brought up this word interfaces. So interfaces is a situation when two different materials meet and they are actually very, very complicated in a real system because very, very small changes in arrangement, in atomic arrangements, even the existence of defects or even strain can completely change how the material behaves. So if we were to do the calculations all by hand using traditional methods, it's almost close to impossible because there's just too many possibilities. Now, AI is really, really good at finding patterns in a huge amount of data. So I think it can help to map out if the atoms are arranged like this, then the materials does that. So we are already seeing this in my group's work on oxide surfaces as well as laid materials. So the breakthrough I'm actually most looking forward to are the following. For example, if I can combine this new magic combination of interfaces that suddenly makes these materials a much better material for example, storing energy, conducting electricity, or in catalysis, even speeding up the materials reaction. So I think discovering combinations in a much data intensive, in an AI agent guided way is really, really good. And another way that I think is really nice is to find ways to create stable, ultra-thin layers for flexible screens, wearable device, ultra-efficient fuel cells, or even potential applications in biomedical engineering. So basically, AI can help us unlock materials which we never even thought was possible before. Thanks for this great question. So we are actually getting closer, but I must say we are not fully there yet. So like right now, some AI systems can already run parts of a research project on their own, suggesting the next experiment, adjusting certain parameters and settings, or even writing a simple report, and that's impressive. So in my very recent review paper with a couple of researchers from Japan, China, and Korea, we look at how AI agents could help design better battery materials, and the early versions are quite impressive. So I guess we are still not there yet, quite a few years, but very close from having agents, AI agents, that feel like true long-term research partners for most research scientists. I think the biggest challenge here, there are a few. Number one, we need to make AI explain its thinking more clearly so that humans can firstly trust and then also understand. We do not want to use them like a mysterious black box. And also, I think we need to make sure it does not make mistakes, right? So it doesn't mean it's AI and therefore it's mistake-free or error-free, because sometimes we have bad or incomplete data, and that's actually a problem. And I think lastly, we need to teach it to combine real experimental knowledge with creativity, not just some repeating patterns we've seen before, and we need to get the science right. So once we solve these problems, I think AI could really, really, really be a smart colleague that never gets tired. Yeah, it's actually my honor. So I actually joined AI Agent because I truly believe that AI is going to change how we do science. I think this is a common belief that many of us share, especially in my field and in many others. So over the years, I think I've moved from doing everything with traditional DFT calculations to now including AI as a partner for my research. So being part of this journal that focuses on this exciting change, it just feels very natural. And it's also a chance for me to make sure that the best and the most responsible AI work gets published and seen by the greater community. So what makes AI Agent, this journal, so special is that it is really, really focused on AI that actually helps make new scientific discovery, not just AI for the sake of AI, I think. It brings together computer scientists, domain experts, like material scientists, chemists and physicists, to share real and useful advances. It's a place where people can actually publish serious and high quality work on how AI can really speed up breakthroughs like clean energy, medicine, new materials, and it encourages openness and reproducibility. I think all this in total combination is quite unique and is very valuable right now. Great. I think this is a very, very suitable question because it is now very important for us to focus on AI for science. So a really strong paper, typically to me, contains three things. Number one, I think it clearly shows how AI solved, or perhaps in the process, helped to solve a real materials problem that older traditional methods cannot handle easily. I think that's number one, to highlight this clear role of AI. And the AI part is done really carefully. You need to ensure good data, proper testing, and also honestly reporting what works and more importantly, what doesn't work, because we can all learn from this. And thirdly, I think it explains the results in a way that makes physical or chemical sense, not just the number looks good. So I think the best paper would also talk about what could be done next, like what idea could actually help the real world. Now, I think people who are new to this area, I think you need to watch out for a few common mistakes, which I see sometimes when handling manuscripts. I think some people treat AI like magic. They don't throw in just data and then without understanding the science behind the problem, and that's actually a very bad practice. So don't treat AI like a black box or like magic. And another situation is where people use really small or sometimes even bad quality data, and then they claim amazing results. Now, this happens a lot, and it usually doesn't hold up. And also another area that's really, really, a taboo in our field is not sharing your code, not sharing your data, or even the exact settings that you use. So science needs to be reproducible and checkable by others. Now, last but not least, this is really, really important for AI for science, is over promising. So when you write a good paper, do not over promise. For example, some people say, oh, this will revolutionize everything tomorrow. I think it's better if we show steady and believable progress. So my advice in the last point is start simple and be honest with limitations. Learn definitely the basic physics and chemistry behind the materials first, and then build from there. I think in that way your work will be really solid and respected.